scalar calculus in this case. And you can do this one all in a vector calculus. Any questions?
How do you get the x with j?
I'm sorry?
How do you get the x with j?
X sub j?
Yeah.
X sub j, if I go back, up, I look at the equation,
Oh, okay.
right?
Yeah.
So this stuff here inside here is actually v sub k, v sub j. I'm sorry, v sub k. So you take v sub k with derivative to this guy, you have this guy left. Okay? So let me see if I can have. Is this display good for you guys, or should I try to get the other one? Is this better? Is it clear? Okay. It's easier for me too. So this is the chain rule, and you do it for every scalar parameter, and you have basically terms of this sort. Now, if you have, this is for a single layer. If you have something deeper, there's a cascade, and this chain rule is going to lead you to more of this cascade. So this chain rule actually is going to just go through a chain, and if the parameter you want is not on this layer, but the previous layer, you have to step further and further and further until you get to the variable you want to take derivative with. And the way you broke it down into pieces, cascaded pieces, and you only compute the derivative between two related things. That's what the chain rule helps you with. So if you have a multi-layers and you're interested in the final weight, you get something like this. That weight, you take derivative at this point. But imagine you have multi-layers and you want to have the derivative of the initial, of the first layer weight. Then you have to take the derivatives through functions of functions of functions of functions until you get this variable, and you have a cascade of things. And we'll see it more compactly when we have, more basically vector calculus. So let me see if I didn't miss anything here. So if you look at the picture of what it is that this gradient descent is doing, you should try to transfer your thinking between the discrete and the continuous. Because in the continuous, when you have that cost function, loss function, that function is going to be viewed as a function of the variables of interest, which is in this case, the weights. So you have an error square, but then that error is a function of the difference between the output and the desired value, and then the output is a nonlinear function of an input, and the input is a weighted sum of other signals, and so on. Okay? Your variable of interest is the weights. So if you want to visualize it, you say, okay, I have this error, and we'll call it epsilon. If I'm viewing this epsilon as a function of E, this is L2 norm. This relation between epsilon and E is convex relationship. Meaning if I plot epsilon versus E, I'm going to have basically something like this, something like x squared. That's convex, meaning there's a one minimum only. Everything goes to that one minimum. When you view this epsilon as a function of the final weights that are here in this case, you look at the complexity of the function, this relationship, because of nonlinearity, the surface is not going to be convex. It's going to be non-convex. So we are dealing with non-convex optimization. Most of the optimization that people address in engineering, in a way, it focuses mostly on convex optimization. So the surface could be so horrible, and maybe here I'm showing you some simple things, but could be worse than this case depending on the how the depth of this network and what have you. And you could obviously have local minima. Here's local minima. This is the global minimum. This is another local minima. You have local maxima. You have inflection points. You have something called saddles, which basically things go to it, two sides, and away from it, other sides. You have a lot of different things. The key thing for gradient systems, you only have minima, meaning minimum. You only have equilibrium, resting points. You either have minima or maxima or a reflection point or a saddle. You don't have other complex things that we see in engineering, for example, oscillations or chaotic behavior. That's the beauty about gradient system, that basically, mathematically, if you're dealing with a continuous gradient system, the complexity of dynamics is limited to only equilibrium. Okay? So that's point one. If we do the update in discrete form, so think of yourself maybe starting some point here, and then depending on the stepping, you could be stepping from here, and I have you could miss that point. If you're here and you're stepping too large, you could miss that point. So the idea is that maybe initially you can have large stepping, but at some point you want to have the steps that you take for the gradient descent be small, so you converge to near minimum point. So now we're going to take a diversion a little bit and look at the concept of gradient systems. I want to pick up some basic notions of gradient systems because the learning technique is going to be gradient descent. We need to understand some basic properties so we don't make any big errors. You need to have some intuition that helps you in making sure you're not making wrong choices. So the concept of gradient system is very simple. You have a variable, it's called x. This variable, in general form, we view it as a vector, okay, n-dimensional vector. We have associated with this variable a scalar quantity. We call the energy or the loss function or the cost function, E, okay? And then we take the partial derivative of that scalar function with respect to this variable. This x now is like the weight in the previous discussion. So I'm abstracting this when I'm just talking about gradient descent in general, not necessarily for neural networks, right? So I have a variable which is going to happen to be my weights in this neural network, but now this is my x variable. And gradient descent or ascent, depending on where you put a positive or negative. Negative, that means you're going to a lower, from one energy level, one cost level, you're lowering the energy level or the cost level. You go into a lower cost function. But equally, you can move to a higher cost function. You can go to the maximum if you want to. So typically, this E represents a surface in the higher dimensional space. We visualize it by something like this here. And the gradient represents a vector. That's how the gradient is a vector in this dimensional space, is anchored at some initial point, and it gives you direction where you're going to move next. That's what the gradient does for you. To give you a flavor about gradient systems, let's take examples, okay? And let's take an arbitrary example. Say, okay, my variable x is a scalar, and just some scalar, and I'm going to square it, 1/2 it, and this is going to be my cost function, it's a scalar function. And this is going to be a convex loss function, because when I plot this x squared over 2, it's going to be something like this. This is E with respect to, this is a convex, meaning that you start anywhere, you're going to go to this global minimum. Okay? That's not the problem we have, but this is an example of a gradient descent. Guarantees that you're going to move to that global minimum. And the way you extract or generate the gradient descent, you have a rate of change. This is mathematically derivative of x, which in practice we represent by delta of x, discrete. And we have the gradient descent. You start here, the arrows show you that you're going to go to the bottom. And you have a global solution. Okay? You can quickly look at another example. The opposite. Put a negative sign, the surface is going to be like this, and the descent will be going away from the maximum. This particular example, the reason I have it, I want to show you that gradient descent could actually go to minus infinity. There's nothing that says it's bounded. Okay, you could just, this function here, if you simulate it, will be going all the way negative. There's no lower bound for it. Okay, so that is a simple example. If you create a function like this, which has this negative and this is positive, this is square and this is fourth power, you can reshape the cost function to make sure you create two minima and one maxima. You have another cost function, which is cosine of a variable, and when you plot this, you have a minimum and maximum. Okay? So, in a nutshell, gradient descent is you have a variable, and you have associated with it, you define a scalar associated with that variable, and then you take the partial derivative of that scalar with respect to the variable. You put a negative, becomes the gradient descent. Become a positive, becomes a gradient descent. Moreover, you could also create gradient-like systems whereby you have the same variable and you have another variable y which relates to x and related by this nonlinearity. Okay? So I'm walking around some of the features that we can see in neural networks because these examples become reminders of behaviors. Okay? So what is the value of gradient descent? The gradient descent is basically if you choose an energy which is radial function, which basically is defined mathematically by another function called class K function. I'm just throwing those things for documentation. But basically, this function has to be bounded below. Okay? So we don't have this other scenario where it's not bounded below, it goes to minus infinity. If it's bounded below, and you have a function that bounds it from below, some beta function of a certain class, then when you start anywhere in a continuous system, you'll be converging to some local minimum. And the reason we throw this gradient descent is that it keeps us away from all this other stuff that we see in physical systems, such as chaos behavior, periodic behaviors, oscillations, all this other stuff, which we don't want. So that's why we choose gradient descent. However, this statement of converging to local minima is 100% true for continuous systems. If the change you have here is actually derivative. But in engineering, often we replace this derivative by a delta W, delta X, which means discrete. In that case, you could generate complex behavior. And the saving factor becomes the eta, which is the strength of this basically descent. So you can have scenarios where you can have dynamic behavior for discrete systems that are not present in continuous systems. So what do? We use the continuous system to build our intuition and to know what to expect. We look at the surface basically as the canvas where we can see behaviors. And we note that our dynamics is not going to be trajectory, continuous trajectory, but actually jumping and stepping. And therefore, a lot of different dynamics could happen in this process, including oscillations and stability. So you could see, when you simulate on a network, if things are not correct, you could have things that oscillate and not give you a solution, or even showing you some very complex dynamics. Why? Because perhaps your eta, which is the step size, is too large. The minute you bring that eta below some level, whereby your simulation becomes representative of the continuous systems, becomes like you solve the numerical problem. So it's like you have a differential equation, and you have discretize it, you simulate it. You could, if you don't take care of the numerical calculations, such as the step size, You could have other dynamics that doesn't represent the system. Okay. Any questions? Excellent. So the gradient descent says we're going to be, if this rate of change of the gradient is actually negative or below some level, you'll be decreasing the energy or the cost at every step. You're improving at every step, okay? And then you could actually go to a so-called equilibrium. You sit at some equilibrium. But this equilibrium, whether the surface that I draw here, I'm showing you a surface which is concave, right? Things are. But you could also have a problem where in some region the surface is just flat. Where solutions go and just once they get on that flat thing, they just stay. They can't move anymore. Okay? So what determines the property of the minimum that you're seeking? So the gradient descent is the first derivative. Okay? Like we know from simple functions, the derivative, when we have a function and we take its derivative and we set it equal to 0, we're looking at all the values, or either min or max or reflection points. That's what we do, right? How do you determine whether it's min or max? What do? You take the second derivative, which is in general form. If the function is a function of multi-variables, that second derivative leads you into a matrix of second derivatives. And that's called the Hessian matrix. So the Hessian matrix determines whether you have a concave or convex shape of near that equilibrium, which means it's minimum or maximum, okay? If it's flat, then the curvature becomes 0. If the second derivative is 0, then basically you have a surface that's just flat, and the minute you get to one point, you just get stuck there. You can't move anymore. So often you like things to have a curvature that's non-zero, and you have it convex, locally convex, and the second derivative controls that, and the second derivative is referred to as the Hessian. And it's a matrix. So in the scalar form, if the second derivative of a function is positive, we say that that point is a minimum. If the second derivative is negative, we say that point is a maximum. If it's 0, we say it's degenerate point. So this is for a single parameter. You have a function of a single parameter. When you have multi-parameters here, you have a matrix. So what's the analog for matrix? I have a table here for you. So once you compute the second derivative matrix, which is the Hessian, you look at what? You get that matrix, you look at whether a matrix is positive definite or negative definite, non-singular or singular. What do those things mean? This Hessian is a square matrix. So when we say positive definite for square matrices, that's another property of matrices that's very useful. We can look at the eigenvalues. If the eigenvalues for this matrix, which is symmetric, and a square symmetric matrix, the eigenvalue is going to be distinct. That's another property of matrices that we exploit. And positive definite meaning that all these eigenvalues are going to be positive. In that case, you say, I reach a local minimum. If some of them are 0, you say I have a degenerate point, because some directions are just basically flat, and some of the directions are concave, and others basically flat. So my point is, for the Hessian, because it's symmetric, when we say positive definite, we can find the eigenvalues and find the properties of eigenvalues. The eigenvalues are going to be real for symmetric matrices. That's another property of symmetric matrices that we invoke. And therefore, we look at these eigenvalues, distinct eigenvalues. If they're all positive, we say it's positive definite. All negative, it's negative definite. These give you whether the point is min or max. If it's stable, that means it's a sink, which is a minimum, local minimum. And if it's unstable, if it's all negative definite, eigenvalues are all negative. Okay? Why am I saying all negative? Because the eigenvalue is also real. We don't have any complex eigenvalues from symmetric matrices. Another wonderful property of symmetric matrices that we invoke. And if some of the eigenvalues are negative and some are positive, then you are at a saddle point. You have some directions are convex and some of the directions are concave. And if it's singular, that means basically it's flat surface. Then you just go and you sit on that flat surface. So these are from basic matrix properties that we're invoking here, and very powerful when we are looking at this case, that by definition the Hessian matrix is always a square symmetric matrix. Okay? Any questions? Okay. Now, this machinery of gradient descent, and actually it is the stochastic gradient descent that we're playing with, even though we do the calculation deterministic here, we always think in terms of stochastic, is the horse of learning technique of everything we have so far. All this deep learning stuff, which really have a depth of layers, okay, uses a variant of gradient descent, the variations, okay? And you'll be learning more of these variations of properties, and these libraries have different versions. And some of them basically, they struggle to say, okay, you gave me this eta, which determines the amplitude or the strength of this descent, and how should I select that? Well, the intuition says select it large at the beginning and then small at the end. That's historically what the intuition is. And people have developed techniques of having this eta becomes a variable that depends on measurements, okay? So I have it updated, and that's what enhances the quality of this learning technique. There's another learning technique which its insight comes from neurobiology, and it started in 1949 by Hepp. And Hepp is a neurobiologist, and the observation from neurobiology focusing on the synapse, how the synapse strength changes. I'm reading basically the quotation here is that when an axon of a cell A is near enough to excite another cell B, and repeatedly and persistently takes part in firing it, some growth process or metabolic changes take place in one or both, such that A's efficiency or efficacy of one cell firing B is increased. So this has been interpreted as there's the connection between two neighboring neurons, which is localized in the synapse, strengthen, okay, if there's a correlation in a way between the firing and one or the other, okay? And to tell you on the outset, there are a lot of different variants of interpretation of this statement. There are a lot of different mathematical models that were created. There's models that actually look at the timing of firing. So they have the presynaptic firing in relation to the postsynaptic firing, before and after the synapse, and they see which one is, if one basically has a causal consequence to the other one or not, and they create a formula, okay? So we're not going to be using these formulas here, but there are people who are using it mostly in some neurobiological things. Nothing has been shown that has a very strong practical evidence. So in some cases, for the engineering, for the application that we're seeking, we're going to be sticking to the domain of the families or the variants of the stochastic gradient descent. Okay? So what we saw right now is the raw stochastic gradient descent. We gave you a variable called eta, representing the strength, and a lot of fancy stuff in defining that eta to improve the performance. So according to my clock here, I have 5 minutes. Any questions? So there is another technique which comes from stochastic gradient descent, which we just derived right now, and has been very popular initially was in machine learning, neural networks, and then signal processing, and has been shown to be very powerful engineering, and is referred to as the least mean square algorithm. And my intention is to show you that actually this is derived from the stochastic gradient descent, and it's a special case. Often in so-called filtering techniques or signal processing techniques, we limit ourselves to a filter which is represented by a single layer. So you have an input, you have a weight matrix, applies that vector input, sometimes maybe plus a vector bias, okay? And you have an output, which is represented by this equation. This is in a scalar form, and here we're showing a dot product between a vector of the components of the weights and a vector with components inputs to have a single output. So this is, and nowadays we interpret this filter as a single layer, because you have input, vector of input, and it's really a scalar output. And the so-called gradient descent, which we describe, actually derived that so-called least mean square algorithm. And the reason we want to bring it up, number one, it relates to it. Number two, the least mean square algorithm has grown on its own merits. It's been a computational power horse for signal processing for many years and has solved many good engineering problems. And it's what it is, it's really a single layer neural network. And the way to specialize the gradient descent is by, again, looking at the error we define as we defined before. I'm limiting myself here to a single scalar output and a vector of inputs. And we define the same loss or cost function or index or energy. I'm throwing all these terms because people from different disciplines, they favor one word over the other. They all mean the same for this case, and it's a scalar function. And it's represented by L2 norm here, 1/2 of this expected value L2 norm. We insert the expected value because we're viewing the data as random process. And then this error square is nothing but desired minus y square. And then what is y? You write what y is, which is this one here, a dot product between a vector w and a vector of input. This is just a compact representation of this whole expression here. And then basically, you take the square quantity and you square it. You have a scalar d square, and then this one will be 2 dy. You just expand that. And keep in mind that the expectation operator is just linear operator. You just walk through this summation, and you need the expected value of each one of those terms. And then you say, what are those terms? This term is a square mean of the value, desired value. This is the cross-correlation function between the input x sub k and d with a parameter. And this is the autocorrelation of the input signals. And note in this case, we're assuming these weights are fixed, and therefore I can apply this operator through it, and I have the weights like that. So far it's the same as the gradient descent. I think I'm going to stop at this point because of time. So I ask you to read the stuff when we finish up this thing on Thursday, okay? Thank you all for your patience. I didn't have any questions today for some reason. It's too simple, or?